that's true at some point in time. So how do we define sets? Because I've just listed out a few sets, and what I've done is I've given you every element in the set, and I've just said my set is the set of bits. First, I described it, and that's enough. You knew what I was talking about. And then another way that I gave it to you was I listed the two elements, 0 and 1. Then I described a set in another way. I said all the two-digit perfect squares. And then I also defined it by just giving you each element that's in that set. And both are fair. And so the listing, that exhaustive listing of all of its elements is a valid way to describe a set. And that's called exhaustive enumeration. And when the sets are very big, it would be exhausting. So for instance, I can't use that. I can't use exhaustive enumeration if I wanted to define for you the set of all prime numbers, because I would be here for a long time and die doing it. That's not good. Okay, so, but there are some sets that we can, and they're the ones that uh, I've previously listed. But this set of prime numbers, it doesn't work. We can't exhaustively list the set of prime numbers. I can list, this is okay. I can list the set of even prime numbers. I can list the set of bits. I can list the two-digit perfect squares, but I can't give you an exhaustive list of the set of prime numbers. So I need another mechanism to do that. Just like summation notation was developed, notation in order to describe that set better was created for a more abstract description. And this is called set abstraction. You can define a set by specifying the condition that must be true for an element to be a member of it. So essentially, I'm going to create a condition. We call that the predicate, and we're going to cover predicates when we get into logic as well. So you'll remember that kind of coming back. But it's a condition that's true for every element in the set and false for every object not in the set. Okay? So, for instance, if we think about the set of students in this class, the set abstraction, the way that I would use that is the predicate would be that you are registered for CSCI 1315 at Dalhousie. Okay? That's a condition that must be true for every element in the set, and it's false for every element not in the set. Okay, generally, we think about a universe, and the universe is all the possible elements that might be considered when we talk about this description. So this condition applies to a certain set of objects. So for instance, if I was talking about the set of students, generally I would restrict my universe of consideration to not everyone in the world, but all of those students that are registered as Dalhousie students, right? That would be the universe of consideration. Okay, and we'll see examples of that. And once we have that universe defined, then the way that we describe the set is we say X is in U. It's part of a member of that universe. So in our example, X is a student, a person is a Dalhousie student. That's the universe, such that this condition holds P of X. And P of X in our case is the student, the person is registered for CSCI 1315. Okay, and I'll show you examples of all the same things that we've covered. So that just denotes all objects X in U, which we've already defined, that set membership, all objects X that are a member of the universe U, for which the predicate P of X is true. Okay, that's very formal, but when you start thinking about what that means, it becomes a bit more clear. It's just a notational formality, but the concept is you describe the set of things that you're considering, and then you find a condition that must be true for them to be a member of the set and false if they're not. Okay, so here's some examples that we've already seen when we talk about set abstraction. The set of bits. Well, this looks very different than writing 0 and 1, doesn't it? So this is, it gets easier. I do promise it does get easier with practice. Yeah. Yeah. And so, and that question about the universe can be infinite? It can be, because my universe in this case is a set that is, the cardinality of that set is infinite, right? It's an infinite set. I just said that the number of integers is infinite. So in fact, if I were to write, the set of bits is a number x that's an integer, so can be positive or negative. It's in the set of integers. X is an integer such that, and this is how we read that double colon, x is an integer such that x squared is equal to x. So right away, I can throw out the negatives, right? Because if I square a negative number, I get a positive number. So I don't even have to think about those. Think it through, yeah? So -1 could be a contender, but -1 times -1 is +1, which is not equal to -1. The only two element integers for which this holds, and you'll have to think about it and prove that to yourself, are 0, 0 squared equals 0, and 1, +1. 1 squared equals 1. And so this is an abstract notation for how we can define the set of bits. So this is still just equal to, and I'm going to use just regular brackets because I can't apparently write them on this screen. 0 and 1, or 1 and 0, however you want to think about it. Okay, now we can describe the set of prime numbers. And now this might seem a bit trite, the way that I've said it, but it's defined, right? We know what prime is. So x is an integer, and x such that x is prime. Okay. The set of even prime numbers, x is an integer such that x is prime and x is even. And of course, we can formalize this, right? And x mod 2 is equal to 0. I think of the percent sign is equal to 0. So the set of 2-digit perfect squares, those are all the integers such that the square root of x is also an integer. That's something to think about. It means that if I take the square root of x, I still get back an integer. It's a perfect square. And it's a 2-digit number. So another way of saying that is it falls between 10 and 99, inclusive, in the closed interval between 10 and 99 using our notation. Okay, the other way that I could define that is I don't have to use x is in z. I can say it's x squared such that x is in 4, 5, 6, 7, 8, 9, because I already know that's a reality. So there's not always one defined way to describe a set. And so sometimes sets are equal and you don't even realize. So there are two important names for sets that I'm going to give you. This one I would argue is the most important, the empty set. Another word for this is the null set. Okay, it's right here. There's nothing there. Okay, well, there it is, the empty set. The empty set, sometimes referred to as the null set, is denoted as my joking 0 with a line through it. It doesn't contain anything. It's the set that contains no elements. Okay. One way that we could describe that, if we wanted to use set abstraction, so this is the exhaustive list. Whoops, wrong screen. This is the exhaustive list, done. There's nothing in it. Or you can say it's all x, I mean, pick a universe, such that, and this is my predicate, false. Well, every time that's true, add the element to the set. Every time it's false, it's not in there. So there's no element that's a member of that set because false is never true. Okay, that's a cheeky description. And so the cardinality, I would always write it as just use the exhaustive list. It takes no time. Okay, so the cardinality of that set is 0. It's still a set, it's just empty. It's something to get one's head around. Okay, another, and this is kind of a side note, but sometimes you'll see the word a singleton set. That's also a special set, and it's just a set that contains exactly one element. And so there's only one thing in existence that meets that criteria that's very unique. And so they have a name for it. It's the singleton set.